Good evening, students. We're going to continue our talk about dynamics, dealing now with angular dynamics. So we've got, again, a nice starter game with a sprite representing, in this case, a ship. We've got it set up so we're going to initialize, load content, basically everything much like the last couple games we've created. The biggest difference here is we're now using a little bit of wrapping to make sure that this stays on screen, just to make it easier to see what we're doing. So we pull out the viewport from the game, and every time we reach an edge of the screen, we just wrap around and start on the other side of the screen. The rest of this is pretty much exactly like the last tutorial we took a look at. The other difference is if we look at our ship, we now have two rockets which are off-center. They're on either edge instead of being centered under the center of mass like we saw on that last ship, the lunar lander example. And because of that, when we have force, this red arrow being applied from one of these rockets firing, it's going to be pushing forward, but we actually have some of that force is going to move us forward. Some of that force is actually going to cause this ship to twist. And we call that twisting force torque. And we can calculate that based on the vector from where that force is pushing on the body to the center of mass of this body. So in this case, I'm putting it somewhere right there, kind of in the middle of the cockpit. So part of this force is actually used to shove the ship forward, and if we wanted to know what that was, we could actually do the trigonometry that would tell us. So if we draw a right triangle here, this leg is actually representing, or this x component of this force, or the x component of this, multiplied by the force, that's going to tell us basically how much of that is being applied as a lever arm, so being twisting, applying this torque. And that's basically the cross product of these two vectors, and the component that goes this direction is actually the forward thrust, so the amount that's actually pushing the ship forward. And we could go ahead and start implementing that in this game. So first of all, we will have linear motion, as we just kind of discussed, and we could calculate that out. We could do the trigonometry out of it, but the nice thing about this is that it is going to be constant, at least the way that we're writing this game. These rockets are either on or off. They're one-speed rockets. They're not going to adjust the amount of thrust, especially because we're using a keyboard. Now, if we were using a controller, we could, for example, maybe use the triggers to be those rockets. If we did that, we could actually generate a varying amount of thrust by how far down you're pulling those triggers, because that actually gives you a floating point number between 0 and 1 as the state. So there are ways you can actually tweak this to actually make it have varying amounts of force, but in our case we're just going to treat it as a constant. So I'm actually going to declare some constants up here at the top, and I'm just going to call linear acceleration, and I'm going to set this to 40 for now, so 40 pixels a second. That's how much acceleration we're going to see based on the mass and the force of this thrust against the rocket. So again, if we wanted to do this more scientifically, we could actually figure out how much force this rocket's generating divided by the mass of the ship. That would give us that acceleration rate after we've scaled it based on how much of that's being applied as torque and how much is being applied linearly. But we can also just plug in a constant and run with that. So if we come down into our update method, we can determine if we are actually accelerating, if those rockets are firing. I'm going to map these to the left and right keys. So if the left key is down, we're going to assume we're firing the left rocket, and if we're firing the left rocket, we're going to apply an acceleration. Vector 2 acceleration equals vector 2 dot unit y, but we want this in the negative direction. So actually I might just go ahead and do a new vector, and we'll do a unit vector scaled by our linear acceleration, and we'll go ahead and make that negative so that we're moving up the screen, because that's the direction our sprite is currently pointing. So that's going to be our acceleration in that forward direction. Now, if the left key is down, there shouldn't be any acceleration, my bad, to start with. Now if we're thrusting, then we're going to be thrusting in that direction we just talked about. So we'll take our acceleration vector and we'll add a new vector 2 in that direction. So the x we're not going to mess with, we're just going to increase the y, negative linear acceleration. And we'll do the same thing for the right key. So if either rocket is firing, it's generating the same amount, because they're the same size rockets, same amount of acceleration in that forward direction. Now that also means that if they're both firing at once, we're generating twice the amount of acceleration, and that's exactly what we want. So here we're basically saying if we're accelerating, we're increasing that value by this amount in that direction. And then we have to do our linear dynamics calculations, so we'd say that our velocity is going to be the plus equals that acceleration times the amount of time that that acceleration has been applied. And then our position is also going to change by our current velocity, scaled by the amount of time that that velocity has been applied. So that's going to give us, get our ship moving forward. So if I fire one thruster, we start moving, fire two thrusters, we start moving. That's maybe a little fast for what I'm shooting for here. So I'm going to crank that down to maybe 10. Let's try this again. Okay, and you can see we're starting to move fairly slowly. We get both of them going, we're going to speed up a lot faster. We're not going to ever really slow down. If we wanted to slow down, we'd basically have to spin our ship around and fire our thrusters the opposite direction, which is actually how you do it with a rocket ship in most cases in the real world. Okay. So that's just linear dynamics again. We've already seen this. That's not the interesting thing. So let's actually look at what it takes to make this rotational dynamics. And we're going to add some more variables. And actually, these probably shouldn't be public. These should be private. But the variables we're going to add are the equivalent of this position, velocity, and then also acceleration eventually for angular motion. And we're going to use floats for those. And the first is the angle. And this is how much rotation our ship has, and it's the equivalent of the position vector for linear dynamics. And then we're also going to have a float angular velocity, which is the equivalent of velocity, only for angular dynamics. And that angle, in order for that to be meaningful, we actually need to rotate the ship and apply that rotation when we draw it. So we're going to actually tweak how we're drawing our ship as well. So we have to use a different draw method, which all of the bigger overrides have a source rectangle we need to specify. We're going to say null. That way we say we're still using the whole sprite. And then we have the float rotation. This is really what we're after. We're going to put our angle there. We also need to define an origin vector, which is basically the center around which we're going to rotate. So if we use this kind of position that's right at the center of the ship, we need to declare a vector that's going to get us to that point. And I'm going to use the vector 30, 39. So our ship is about 60, and actually when I do this, it's about 39 tall and 60 wide, so that's actually going to put our center of gravity right back here, or center of rotation there, which I think I like that, so I'm going to leave it there. We could also push it forward some. Then we need the scaling value, which is going to be 1 or 1f, and then we need our sprite effects. We're not going to do anything sprite effects wise, so sprite effects none, and a layer depth of 0. So basically the defaults for everything except for this origin vector and the angle. And the result of doing that is now we can actually rotate that ship. Alright, so we have our angle, our angular velocity. When we generate our ship, we're going to actually set that one more. We need a direction vector as well. Vector 2. Direction, and this is the direction that the ship is facing, and it's based on this angle. So these are related. This is basically if we were to draw a triangle, a right triangle with a vector out of the front of the ship, the angle would be, here would be the hypotenuse would be the vector, and the x and y components would be the legs of that triangle. So we go ahead and create our direction, and when we create our sprite, we're going to have that direction pointing as a unit vector in the upwards direction, which is going to be minus vector 2 dot unit y, which is basically 0, -1. Now if we come down and get into our acceleration, this is where we're going to start looking at how do we generate that acceleration in the angular dimension. So this is going to be our angular acceleration. We're going to start this one at 0, just like we started the acceleration vector at 0. But now we need to calculate what this is going to be based on this incoming, the fact that we're thrusting with that engine. So when we thrust with that engine, part of that again pushes the ship forward. Part of it is going to actually cause torque, which makes the ship rotate. And to find that torque amount, we take this vector to the center of the ship, that vector r, and we're going to cross product that with the force vector. So we need our vector r, which is going to be a new vector 2, and we'll go ahead and set this to be 76 and 50. That's my old values. Basically want this to be the same as this, the 30 and 39. 30, 39. And then we have our force vector. And let's make this be 0 and 2. Or maybe 20. We'll try 20. And then we can calculate the torque. And the torque, in this case, is the cross product of these two vectors. And the cross product, we calculate cross product we calculate with force dot x, the x of one, times the y of the other, plus the y of the first, so force dot y times the x of the other. And that's why it's called cross product, because we're crossing the components and multiplying them. And once we have that torque, we can say that our angular acceleration is going to increase by that amount of torque divided by the moment of inertia. So the moment of inertia is the equivalent of mass for angular force effects. It basically is how much this ship is going to resist being turned. And what we'll do is we'll actually just assume it's 1, and we'll actually account for that just in the strength of our force. We could also actually calculate it out and not try to account for it that way. That's fine. We basically do the same thing when we're thrusting with the other engine, but with the other engine, our r vector is going to actually be in the opposite direction. So the 30 would be a -30. Or we could just invert the torque, because that's the end result of what that would be. Okay, so now we have our angular acceleration, and the calculation we do with that is very similar to what we're doing with the linear dynamics here. So we're going to take our angular velocity, and the angular acceleration is the change in that angular velocity over time. So we could say angular acceleration times t, and then the angle is, or angular velocity is the change in the angle over time. So we can take that angular velocity and multiply that by t. And the result of doing that is we're now going to have the new angle. And along with that, we need to calculate our direction. Which is going to be the sine of this angle is going to be our x component. and the cosine is going to be the y component, and I believe we need to also invert this because our coordinate system is inverted. And if we did that correctly, then we should, when we run this, actually see if we accelerate just one engine twisting, other engine twisting the other direction. So I have some values pumped up way too high for that to be spinning quite like that. So let's tweak our values some. Value do I have up too high? 6. Oh yeah. Let's take this force down to 2. There we go. If I push on the right engine, right engine, left engine, that's still quite a bit higher. So we basically could take this torque and divide it by, say, 50 to account for our moment of inertia. If we run that, there you can see we're starting to get slower motion. Now, like I said, to avoid this calculation, we could actually push that up into the force vector. So if this goes even smaller, say dividing this by 50 would be 0.1, I think, if I'm doing my math in my head right, which I'm probably not because I haven't been getting as much sleep as I used to. But that should, if nothing else, slow us down. Yep, so you can see we have a little bit of acceleration. Now the other thing we need to worry about is that if we're twisted and we accelerate, that twisting should make our acceleration go in the direction we're facing. And that's why we are actually calculating this angle direction vector, is because that determines the direction our ship is facing, and we want our angular acceleration to actually be applied in that direction. So what we're going to come back in here and do is, instead of using this vector scaled to our linear acceleration, we're going to do the direction vector scaled to that acceleration. And I believe we don't need this to be negative anymore because our direction is going to account for the actual direction we're facing. So let's try that. So if I turn the ship a little bit and then I accelerate, it should start accelerating in the direction I'm facing. If I accelerate opposite the direction we're facing, whoops, slow down. There we go. So now you can see we're flying forward, and I've got a little bit of rotational velocity still going, so I'm kind of spinning as I'm moving forward. If I want to turn around, I basically have to re-rotate my ship, face the opposite direction so that my thrust is opposite the direction I'm facing, which is actually challenging to control, just because you have to account for the direction you're facing and mentally rotate those controls. So that's the basics of applying angular motion, angular dynamics. Now, there is something, if we look at this, there's an easy optimization we can do here, because we have this r vector is not actually changing, this force vector is not changing, our torque is therefore also not changing. This is all constant. So we could replace all of this with a constant value and apply it just like we did with the linear acceleration. So if we were going to do that, we'd declare another constant And let's set this to 5. We'll try that. And then if we come down in here, we basically just replace all of these guys. So instead of calculating the actual torque and applying it to our acceleration, we just say if we're firing that particular rocket, we're going to see that acceleration scale by applying the angular acceleration. And in this case, it's just going to be in the opposite direction. So minus equals angular acceleration. Now we can do that in this case because those are staying constant. Again, if we were doing a more complex simulation where those were not constants, we'd actually need to calculate them each frame. But because we don't have to here, we'd actually save a lot of operations and get effectively the same effect. So here I have my ship, I apply a little bit of torque, notice I can spin it, I can accelerate in the direction I'm facing. If I manage to turn myself around, I can accelerate in the opposite direction. And that's basically angular acceleration plus some linear dynamics. So we have linear dynamics, angular dynamics, the whole 9 yards. So that gets us basically through how we deal with the angular dynamic side of things. So the next example we'll take a look at is how we actually deal with collisions and collision restitution in 2 dimensions. So if we have 2 objects that smack into each other and have an elastic collision, so one where they bounce off of each other, how would we calculate their new direction and velocity if we were trying to be realistic to the physics that are involved? And that's really all we have for right now, so we'll go ahead and stop it here.